Okay, so I'm continuing to build on my Lagrange point calculations and modeling. And this is where I left off. So I actually calculated the L1 and the L2 Lagrange point, which I'm going to show you in just a second how to get that just roughly, but we can watch the whole video. I'm making a playlist here, so if you want to follow along, that's awesome. Really, I'm talking to myself because I'm going to look at this later. So here is a binary system. So I have two masses that are orbiting each other, and I calculated the Lagrange points. And you'll notice one of the things, here's this, let me rerun this and you can see what it looks like. So I have the bigger star, another star or planet, whatever you want to call it, and then the two Lagrange points right there moving along. And it looks like it's cool and working and all, but there you go, you see it's not stable. And I know that the Lagrange points aren't stable, L1 and L2, but I thought they'd be more stable than that. And so the thing is, I think that the way that I calculated these points just wasn't accurate enough. So it's really not right there. If you get it right at that point, if you get it right at the Lagrange point, it should actually stay. Another problem that I'm having in this case, I use stars, let's see, 2 times, oh, it's smaller. Okay, 2 times 10 to the 30th and 1 times 10 to the 28th, and then a distance of 8 times 10 to the 10th. So, I mean, originally I had them too close together, and I think it's really unstable at that point. But let's switch over to the paper. I'm going to explain how I got that just briefly as a review, and then I'm going to talk about a new method I'm going to use to calculate these. I actually have two different ways I could do this, but let's just see how it goes, and maybe we can make it more stable. So just as a review, the first thing I did in this series was to model two objects orbiting each other where they both have mass. The very, very first time I did this, I said this is the sun and it didn't move, but it does move. So I wanted to be as accurate as possible. So I include both of these objects orbiting in a stable circular orbit around a common center of mass. So if I pick two arbitrary masses, M1 and M2, a distance separated by distance r, I need to find the center mass, put that at the origin, and then find the velocities for these two things such that they have zero total momentum. So that's the R1 and R2. That's the velocity, the magnitude of the velocity that it needs to have to be in a circular orbit. And then this is the angular velocity, which is very important because all of these objects have the same angular velocity if they're moving together. And if you put a mass right here, it's going to have that same angular velocity if it's in a L1 Lagrange point. And that's what the Lagrange points are. They're places around these two masses such that it will move and stay in a position constant relative to really this planet or whatever you want to call it here, but it's constant relative to that one too. So it will orbit right along next to it, and then you could put a spacecraft there or a space telescope, and you know exactly where it's at. So it's a good location. So there's my angular velocity. And so what I did was to calculate the gravitational force on this mass. Well, that's the gravitational force due to this mass right here, and that's its distance. And then there's a gravitational force pulling back the other way due to this mass. And then that has to equal mass times acceleration. It's moving in a circle. So the acceleration is this mass times omega squared r. That's the centripetal acceleration. If you put that together, you get this equation. Now, the one thing that makes this difficult is that all these distances are different, right? This distance for the gravitational force, this distance for the other gravitational force, and then this distance, RL1, for the acceleration because it's moving in a circle of radius RL1. And so you get this more complicated equation down here that looks not so bad, but it's bad. Okay. And so the way I solved this was to just calculate, and the mass of the object right here canceled. It was in every term. And that's the omega squared. See, that's that. So I calculate the left-hand side of this. I calculate the right-hand side. And then I just increase my value of RL1 until this is no longer greater than that. It starts off, if you start at RL1 equals 0, so right here, and you move this way, this is going to be greater than that. And eventually over here, this will be greater. So I look for that point where they swap. Okay. Now the problem I had was I started right here and going to there, and I used 1,000 steps. But if you break this into 1,000 pieces, then that's not a very small size. So I could say move right here and have this is greater, and then move right here, and then that's greater, so that would be my final point. So I need to modify my function that I use to calculate the Lagrange points so that I can do something better. Let me just explain what I'm going to do. So before I started right here, and I moved until the right-hand side, I call this RHS, LHS, until this was less than that, and then I stopped. So that would be moving to right here if it's really close, and then I move a step more, I'll call that DR. Over here, if my DR size is really big, then I could be way off. So what I'm going to do is make my function such that it, before I had the function that I input the masses and R, and that's all I needed to find everything else. And it would return the location of L1. I did L1, L2 also. But it started at R equals 0 and just worked up until I got to that point. And hopefully I'd find a Lagrange point. So what I'm going to do is input the step size into the function, and I'm going to input the starting location. So what I can do is to move this until I get negative, and then go back over here. So I start with a positive value. And then with this, I can put that as my starting location, and I'll make a smaller step size, and I'll do it again. So hopefully I'll get closer to that point, and then I'll do it again. So I can repeat this function kind of iteratively, getting closer and closer to where I should be. That's what I'm going to do. Okay, so let's switch over to our program and make some modifications so that we can get this thing to work. So here I am right here. I'm going to use, let's see, where did I put it? This one. This is the same code, essentially, but it has the function L2 and L1 in there. I'm going to start deleting some stuff just to make it simpler, because I don't want to have to deal with two of these functions at the same time. But this does deal with, I changed the masses here, and so I have R, I have R1 and 1. We can always change that later. And there's star1, star2, initial momentums. This is the function L1. I'm going to get rid of L2. Let's just get rid of that whole thing. I have another copy of that, so it's fine. This is something I did before. Let's just comment that out. I was testing. And rcalc, let's just get rid of that. Let's do that. So ball M, ball P. Ball 2 is for Lagrange point 2. I'm getting rid of that one. And then down here I have, can you see this? It's okay. Down here I have R1B. This is all for R1, right? That's the R1B is from the star 1 to the ball, and R2B is from star 2 to the ball. And then I did the same thing for Lagrange point 2. Delete that. This is the force on ball 1 at Lagrange point 1, and that do the same thing for ball 2. Delete that. And then let's get rid of all this ball 2 stuff, just to make things simpler. And I know it's like, hey, you're destroying stuff. I agree. So a lot of times I would just comment that out, because then I could, it'd still be there, but I want to make the code a little bit clearer. So this updates the position of the ball, the position of stars, and stuff like that. Let's run it and see what happens, because I could have broke something. So it's taken a while because it's going through and calculating that location, and there you go. And you can see, let's just see how stable it is. Yeah, so then it's already going off. Yeah, so it didn't even make a complete orbit. Okay, so down here is my function to calculate L1. I input the distance between the stars and the mass of the two stars. What I want to add in there is, I'm looking at my notes because I forgot how to do this. Let's put this R start, and DR. So down here, I don't need DR. I'm going to comment that out. I'm putting that in as a variable that I'm passing to the function. And RL1 is 0. I'm going to take that out. I'm going to just change that to RL1 equals R start. So now it should work with just those two modifications. So here's, actually I should have written down that number. Well, let's let's just change this to, I need R start. I'm going to put it at 0. And then dr is going to be this. I'm going to put that same thing in. So it should be getting the exact same thing. Let's run it. Okay, so it looks like it's running. It should be unstable at the same spot because it should be the exact same calculation. Yep, there it goes. Great. Okay. So I didn't break anything. That's the key. I want to make sure I don't break anything. So now my function, now I can change the starting location and I can change the step size. Okay. So let's go down here and make some new variables. So the first thing I'm going to do actually is to, I need to do one more thing. I forgot. I need to do one more thing up here. I return L1. And I want, that's the, after it becomes less than, it says if the left-hand side is less than, then return. So I've actually gone past the Lagrange point. So I want to go back one step. So I'm going to go up here and just say return RL1 minus dr. So now it's going to go back one step and return that value. So if I run this, it should give me maybe a slightly different thing. Let's see how different it looks. Because this is actually a different Lagrange point, and you can see how unstable this is, or stable. Yeah, see? Now something completely different happened. So that is that transition point between too far to the left and too far to the right. If it's too far to the right, it gets ejected. If it's too close, it just does this other orbit, which actually looks pretty cool. Okay, so that's good. That's good. Okay, so now I can go down here. I'm looking at my notes because I don't want to forget stuff, because I did get kind of confused making this. So this is the model of the stuff. But before I do that, actually before I do this right here, I want to get a better calculation of this. So let's just get rid of this. I can't make the ball yet because I want to move that location. So what I'm going to do is to say RLS equals 0. This is my location. It's a list of Lagrange points that are wrong. Okay, and this is really my starting location. So I'm going to start with 0. That's where I had before. And then I can add new ones here, and I can refer back to the previous one. I don't know if that makes sense or not. So then I can say, let's say this, n equals 1, dr equals r divided by 1,000. That's where I'm just going to start. I'm going to start with my dr of r is 1,000. So now what I'm going to do is to, let's say while n is less than 5. So I'm going to do 5 loops where I change the starting location and calculate this Lagrange point. And the first thing I'm going to do is to calculate the new Lagrange point. So I'm just going to say R new is equal to the function L1. And I'm going to pass it R, M1, M2, just like before. And the starting location, do I have the start or? The starting location is going to be this. Okay. Watch this. So I want that first element, but I want it to change within. And you can do these different ways, but I'm going to say RLS n minus 1. See, so I didn't start n equals 0. I started it at n equals 1. So the first time I get to this, it's going to say 1 minus 1, and RLS 0 is 0. It's that first element in the list. So that's good. And then I'm going to put dr. Now I'm going to take that. It's going to return a location, and we already know where that's going to be. But now I'm going to take that, I'm going to add that to my list. Now I'm going to have 2 in there. And now what I'm going to do is change dr. I'm going to say dr equals dr divided by 10. So it's going to be a tenth a step. So I'm going to decrease that step size by a factor of 10. And now I'm going to add n equals n plus 1. So I'm going to increase my value of n so that I'll eventually end this loop. And then the last value that I end with is r new. Okay. So I think I can just say let's put this, there's no r calc anymore. So I'll put this as r new. And then let's print RLS equals the whole list. Let's just print all 4 values. It's going to be 4 RLS. Okay, let's see what happens. So I'm going to run it. I'm going to go through and find the Lagrange point. I'm going to go back and do it again and keep doing it again 5 times. I did it pretty quickly. And there's my values. So you can see I had 4.22, 4.22, 4. They look the same. They're actually not the same. In fact, there is a trick. And you notice that it did orbit differently. So it is doing something different. If I go up to the top up here, I can say this, print. I had to look this up on the GlowScript forum. Print options digits equals 15 because it will print out more digits, and let's run it again. And it didn't really matter. It did matter. Okay. So you can see I get better and better answers. Let's see if we can get even better. Let's say while n is less than 8. Let's see how stable that is. Okay, you see right there, it almost makes a complete orbit. Let's try one more, n equals 9. If you get too many loops, you get to some weird stuff happening because your step size is so tiny. But it's doing it fine. Make a loop. Did it. It's, okay, almost. It almost made it. Okay. So that's pretty good, though. I think one of the problems is that... oh, I didn't even look at my list. Let's look at my list. Did it print out? There it is. So there's my list. So there's my value of 1.44 times C. I can't believe that's not perfect. I feel like this is just an unstable system. Let's see what happens if we make this more like a planet in the Earth. And I don't know if this is even going to work. So here's M1 as 2 times 10 to the 30th. Let's change this to 2 times 10 to the 27th, which is still bigger than the mass of the Earth. And let's change this to, it's the distance from the Earth to the Sun is 1.5 times 10 to the 11th. So it's not quite there, but let's just see what happens. It's running slower because the orbits are slower. But you'll notice here I went 7.56 down to 7.563987624 times 10 to the 10th. It looks like it's, well, I don't know if it's going to make a loop. I can't wait that long. I did make the step size smaller too. Down here, 100. Let's be bold and make that 1,000 and see if it still works. It feels like it's getting a little unstable, but I don't know. I made a loop. It's not perfect. They're starting to lose it. Okay. I bet that if I go and make this step size 100, which is tiny, and then increase this to, let's say, 6, so I can have to wait. Let's just see if that makes a big difference. A step size of 100 seems too small for this kind of system, but here we are. I just wanted to make a complete loop. And then I think I might try having one more step size on there. But actually, let's plot the step size. That's what I'm going to do. Come on. Well, I know it's going to make a complete loop. The question is how close. The other one made one complete loop and then diverged. If it makes it down to the bottom of this thing, I'll be pretty happy. So yeah, you can see the step size really does matter. This one already diverged before. It's starting to diverge now, so I guess it doesn't matter too much. Okay, let's go back over here and let's do this. First thing I want to do is this. I'm going to say run this for 0 seconds. That way I don't have to worry about that. And I'm going to make a graph. So let's make a graph. Let's see. I did not make a, okay, let's make a graph down here. So there's my function up here before I do this. So G2 equals graph. And I want to make, let's put on the vertical axis, so Y title equals RL1. X title is equal to N. Right, so I want to see how those things change. And I'm also going to make a log plot. So log y equals true. So this will make the vertical axis a log axis. Then I will say FP1 is that point, and it's this G curve. And I got to put what graph it's on. Graph. I don't know if I have more than one graph in here. And let's say markers. Is that right? Markers equals true. I think that might be right. That puts dots on them. Okay, so now down here, I'm going to plot a data point before I add in. So I'll say fp1.plot, and my x value is going to be in. My y value is going to be r new, right there. So that way we can see how these data points progress. So marker is not an attribute of series. Okay, fine. I'll just take that part out. Dots equals true. I can't remember what it was. Markers. I want to try that. I think it's markers equals true. Yeah, there you go. See? I didn't give it a color though, which is kind of odd for me. But you see here, this is actually really good. You can see that I don't think I need to go another number. This is a log plot. Is it a log plot? 7597. I guess it is. It's just not a very big range. Yeah, it is. So, but you see that it converges to a number really quickly. And so I don't think I really need to go anymore. Maybe a smaller step size would work. But I suspect that what would really do it is just to make the two things further apart. What am I doing on time here? Yeah, so I do have another method I want to try. But let's see if I put these at, let's say 1.5 times 10 to the 11th. Let's just say 10 to the 24th. So I actually, that's even smaller than there, 10 to the 25th. So we're really at Earth-size stuff here. Oh, you know what? I didn't run it because I said 0. Get rid of that. And it's probably going to run super slow. Let's put that at 1,000. And so you'll notice how close it is to the Earth. Let's just see if it diverges. It's going to diverge. This is a question about when. There it goes, starting to diverge. Okay, so unstable, but you see here that we have a really nice slope. I'm pretty happy. Okay, there is another way that we can find this, and it's using like forces and drag. It's kind of like let it find its own equilibrium position. And I want to try that and to be able to plot the stability of this. So how stable is it when you change your R values, so we can see that. And I'll do that in another video. But I'll include this code down below. And it is on GlowScript, not Trinket. So in this case, I think that if you want to edit the code, you're going to have to log in. But I think if you click it, you might be able to just copy and paste it into whatever you want. But I'll add this to my series. My other videos are in the playlist. So I'm going to keep working on this because I don't know why I just get kind of obsessed with things. I still haven't found Lagrange points 4 and 5. I didn't do 3 either, but that one's really kind of boring. I think it worked really well. So, all right, I'll end there. Talk to you guys later.